So, hi again. Homework 3, grading is finished, comments have been sent out. And as you can see, we're still very, very proud of you. You guys are doing very well on the homework sets so far. So this is really great, right? We have all these 9 and 10 points there. So keep up the good work, I guess, is the take-home message here. And just a word of caution, warning, late days. Our policy says you have a total of 6 late days, and you're allowed to use up to 2 per assignment. And if you run out of late days, we'll start deduct points for every day that you submit late. I think it's 2 points. Yeah. So please make sure that you keep track of your late days. The number of late days you used is given in the comment email you get. Like it's going to say your numbers of late days used or something like this. And it's going to give you the number that we deducted for that assignment. And I know this looks a bit strange, so we have a few cases who already used 7 late days, but we only have 3 homeworks graded so far. So what happens is some people try to submit very, very late on late day 2, and they miss the deadline. And our syllabus says that we won't grade those homeworks. What we did instead is, if there was a reasonable margin, we deducted 3 late days for those people, just to give a grace period. But we had to deduct an additional late day to be fair to everybody, because if the same thing would have happened on Thursday evening, right, Thursday night, you would have had to submit to the next late day box. So we still wanted to be fair to everybody, so we deducted 1 more late day in these cases, but we also, for just a couple of minutes or an hour, didn't want to over-penalize students for submitting late. So just be aware of the numbers of late days you used so far and keep track. So then, just for fun, homework 4 has you predict the polls coming up. And Stephanie organized a little competition form that is linked on Piazza. There should be a post on Piazza. And I think it's a form where you can submit your results. This is just for fun, so this is not used to grade your homework, right? This is just for a bit of friendly competition so that you can see how good your predictions are compared to your classmates. So participate if you want to, and I don't think we have a prize yet, right? But there's going to be one? Dinner with Nate Silver. If you beat Nate Silver. So we can at least have an honorable mention. And then we're going to see about the prize. So final projects. I already got a few questions. When are the deadlines and everything? So by now, the project description is linked on the course homepage. If you look there, it's going to be one long document that describes all the deliverables that you have to do. Like we want you to submit, for example, an IPython notebook that has your whole process, like how you came up with your idea, what questions you asked, all of this. So you should have an IPython notebook basically documenting the whole process of your final project. And then in addition, it's a website and a video screencast. And the proposals are due on the 17th of November. And then in the week afterwards, I believe that is a Monday. So on the Tuesday and Thursday of that week, you are going to meet with the TF and discuss your project. What we basically want is you to get feedback early, whether your project is ambitious enough, or maybe it's also too ambitious, right? So you're going to have a TF assigned to your project team. And also then during those 4 weeks that you work on the project, that is your partner to ask questions to, or if you get really stuck, ask for advice. And the idea here is that you meet during the lecture time, because there we could reasonably make sure that all of you should have time, Tuesdays and Thursdays. So during those times, so there's not going to be any lecture in that week. Instead, you meet with your TF and discuss your projects. And then we split the due dates. The project itself is due on the 10th of December. So with that, we mean your IPython notebook. So all the coding should be done until then. and all your results generated, and you submit the IPython notebook with all your cool visualizations and the story you want to tell. And then you have 2 more days to work on your website and the screencast. And we made this so that you can really focus and make this a great show-off work, right? Like, if you later on want to apply for jobs in the area or something, you should really have a web page you can be proud of. So this is going to be public. The web page is going to be public for everybody. And I would like you to use this opportunity to say, here, I'm a great data scientist, right? If I want to apply to a job somewhere, I can have a good feeling just giving them the URL and saying, here, this is what I can do. So this IPython process book should contain the overview and motivation of your project. Like, how did you come up with that idea? What are initial questions you could think of that you would like to explore? Then a short overview of related work. Maybe something inspired you, right? Maybe even a project from last year that you want to build upon. That's okay, but you have to give credit for the work that has been done before and then build on top of it. And the initial questions you wanted to ask, the data, if you scrape something, the code should be in the IPython notebook. All code you write, we're going to look for clean code here, right? And please also document. Like, I know that there have been some homework submissions with variable names with just single letters. Like, please, the final project is going to be a larger piece of code, right? So please write code that is easy to read. And documentation, documentation. So then the exploratory analysis, like after you got the data, right, what did you do to get a sense and the feeling for the data? You've done this in homeworks, you've discussed it in class, and then the final analysis where you actually go ahead and answer your questions. And compared to last year, we focused more on machine learning this year, so it would be really cool if you also have a prediction part, right, in there. So I just wanted to give you a few more examples just to motivate you, what things you could do from last year. And these are these 2-minute screencasts.
It all began a few weeks ago when we, uninspired by our original topic, sat down for a group meeting. An off-color joke, which we won't repeat here, started a debate about relative superiority of group members. Thus, the idea of comparison was born. The 2 subjects to compare long remained a point of debate within our group. From Android to iPhone, to Germany to France, to Hans-Peter Pfister to Joseph Blitzstein, the possibilities seemed endless. PlayStation 4 and Xbox One were eventually chosen as our subjects because we hypothesized we could learn a lot about consumer preferences in these products through Twitter. We used Twitter's streaming API to collect over 600,000 tweets from around the globe over the course of a week. From these tweets, we first looked at the text of the tweet itself. What are people talking about when they mention Xbox One and PlayStation 4? Then we looked at time. We were curious if Twitter users talk about these gaming systems at different times during the day or week. If PlayStation 4 users tend to have the highest rate of tweets at a later time in the day than Xbox users do, Sony might want to consider advertising for PlayStation 4 on TV and other outlets at a later time in the day than Microsoft would. We also looked at what device people post their tweet with. This could be valuable if, for example, 60% of PlayStation 4 users tweet with an iPhone, whereas only 20% of Xbox users do. Then it's likely that the style of advertising Apple employs is much more effective on PS4 users than Xbox users, and Sony should consider making their advertising style more similar to Apple's. We also looked at location, where Xbox and PlayStation 4 consumers are in the world, because this is also of interest. The size of the circle on the maps is proportional to the number of tweets in a given location. We have GIFs of how tweet numbers change over time on our website. Finally, we developed predictors for whether a tweet will be retweeted or not, as well as what country it's from. Over 80%.
So that was a bit too long, I guess, the video. This is why it fades out, so please stick to your 2-minute limit. The videos are going to be shortened if they're longer. I chose this project because I think there's something they did really, really well. Is there something you really liked about their screen presentation? Visuals, yes. Very nice storytelling there. So maybe it's hard to see if you haven't compared different projects. I think they did a very, very good job in motivating their questions, right? They said, we looked at the time of the tweets because this could have implications for this. Or we looked at the device they were tweeting with because this could be important for. So before even looking at the data, they had a motivation and described this very clearly, why they were looking at these types of questions. On the other hand, I actually would have wished they would have more presented results there too, right? They didn't go, yeah, and this came out, so please, Xbox, right, advertise more at this time of day. So, but I think this motivation part, also in your IPython notebook, like, ask why and give us the answer why. Give us motivation why you're doing something. Like, our insight that we want to get is that you understand what you're doing and that you have a guide through your project. So this is the feeling we would like to get from your IPython notebook and also from your screencast. And I think there, with the why questions, they did a really cool job.
For our CS109 project, we set out to predict which Kickstarter projects succeed. The first step was to collect data about all of the projects. First, we found the titles of all of them, and then scraped their features off of Kickstarter one by one. We used the information we had gathered to model about 20 different project features, including everything from the average length of words in the blurb, to the currency of donations asked for, to whether the users used Facebook. Here are the biggest takeaways we have for prospective Kickstarter projects. Projects are more likely to succeed if they have lower financial goals. But independent of goal, your project is more likely to succeed if you set its deadlines soon after its launch. Projects in some categories, like dance, are much easier to fundraise for than others, like hip-hop. And some locations, particularly wealthy Northeast states, have more success fundraising. Finally, buzzwords matter. For instance, if you're kickstarting for a graphic design project, use inclusive pronouns like us and we, rather than second-person pronouns like you and your. Eventually, we combined all our models to see how accurately we could predict the success of projects. Given a set that it has never seen before, our model correctly predicts the success or failure of about 70%. This isn't a ton, but it's a significant improvement over the baseline. Thanks for listening.
Okay, again here, I like very much the outline of the project. You've seen the IPython notebook. That is actually also something I've heard that a lot of screencasts looked that way last year. This is why we did the IPython notebooks due on Wednesday and the screencast due on Friday, because I wanted to give you time to actually spend a bit more effort on the screencast and make it look cool. Because if you scroll through your IPython notebook, right, you've seen you can't really read the code anyways in the video resolution. So you're wasting a lot of space in the video, right? And given that visualization and storytelling is part of the class, I think it just would be a pity to waste like 30% of your screen space there for code that nobody can read. So nevertheless, this I think was a really cool project. Prediction 70%. I think that's actually really cool as a result for such an ambitious project. In total, don't go too crazy with your expectations, right? It's okay if you have a cool analysis in there of the data set and everything. If the prediction doesn't work as well as you would like it to, don't fret, but maybe try to describe to us why you think, or maybe have an idea what you could do to improve the prediction performance if you would have more time, right? Something like this is okay. But for example, we're going to have this one lecture on deep learning. I think I said this before, I don't expect anybody to actually apply these very complicated models, right? They tend to predict very well if you use them right, but it's hard to use them right. And 4 weeks most probably won't be enough. So I don't want you to spend a crazy amount of time trying to get something to work that is overly complicated and not suited to the level of the class, right? Okay, and then I think I have one third one. Yeah, this I really like because they used clustering in there. So there's actual unsupervised learning in here.
The presidency today is not what it was when George Washington took office. However, despite changing times, there are presidents from all periods of American history who are commonly considered great. In this project, we study the evolution of the executive office over time and attempt to quantitatively explain the success of great presidents who faced unique challenges and lived in starkly different times.
When we cluster the presidents based on aggregated rankings from various academic sources, we see that they are split into three main groups: the greatest presidents, such as Washington and FDR, the good presidents, and the mediocre presidents.
Presidential power is often split into administrative, legislative, and rhetorical components. The Siena College survey aggregates rankings for all the presidents based on a variety of attributes. As you can see, the administrative powers correlate more closely with the perception of a president's success, while rhetorical powers correlate less, and legislative powers correlate the least.
We first study administrative power, which includes aspects such as executive orders and vetoes. These graphs show that presidents have increased their use of executive power over time. Many of the greatest presidents, such as Teddy Roosevelt, Woodrow Wilson, and FDR, correspond to large jumps in the use of executive power.
Legislative power consists of the president's ability to influence the decisions of Congress by proposing legislation. Unlike with executive power, we can see that the president's use of legislative power has varied greatly over the years. Surprisingly, we see that there is a slight but significant negative association between the number of papers written to Congress and overall success.
Rhetorical power refers to the president's use of speeches to influence the general attitude of the nation. The president uses inaugural and State of the Union addresses to talk about their general plans for the presidency, and radio addresses to talk about day-to-day issues. And while the words a president uses does not necessarily reflect his skill as a president, they reflect the state of the nation. Popular presidents are able to talk about social progress. Unpopular presidents have to talk about national concerns.
As you can see, a president's success is defined largely by the problems of his time. Presidents who are faced with challenges and take matters into their own hands tend to be remembered as better presidents.
Okay, that was just to give you ideas of like things that you could do, from scraping data yourself to maybe getting data from somewhere, and the type of analysis that we would like you to do. I think this was really cool, showing a story about the presidents and the different types of performances. So take-home messages, I think I've said most of this by now again. So say why you're doing something, give clear motivations for your way to explore the data. It's better to go safe than sorry. Like in my experience as a TF before, most student projects were borderline too ambitious often, unless people didn't have a motivational idea. But if you have something that you're really interested in, that excites you, most people try to go overboard and do even more crazy and great stuff, which is awesome and totally great. It's just, if you, after those 4 weeks, you don't have the results to show, right? We can't really say, well, you tried. So this is why the meeting with the TFs is so important, to stop you in case this is not doable in 4 weeks. Yeah. Okay, that was all I wanted to say to the final project. Are there any questions left about the organization part? Okay, cool. Then we're back to supervised learning. It's the last supervised classifier we're going to really talk about, which is the support vector machine. And we're going to get slowly there by first talking about the separating hyperplane. So with k-nearest neighbors and decision trees, you've seen that the hyperplane wasn't really a hyperplane, right? Like with the k-nearest neighbors, it was implicitly defined by looking at the nearest neighbors, and then we could basically see which places in which locations would be classified as which class, and this is how we plotted the decision boundary. We didn't really plot the boundary. We plotted the classification of every point in the feature space to see the decision boundary. So here now, with the decision trees, we could already plot the boundary, right? Those were the thresholds that we chose for the different splits. But in the very beginning, when I said this is machine learning in 10 seconds, I showed a different picture. And what I showed was your two classes here of data points. And then there was this separating hyperplane. And now we're finally actually going to talk about this case. So slightly different than before. Before we had our labels 0 and 1. And we're now going to switch and make this -1 and +1. And you're just going to see the math becomes easier for this type of classifiers if you do it that way. So we have our separating hyperplane, and how we define it is by an orthogonal vector W. Right? So this vector gives me the orientation of the hyperplane because I just say this vector is always orthogonal to my separating hyperplane. So this is just, Raphael has talked about linear algebra before. So what I have is this weight vector here, W. And these are my points X from my data samples. So if I say the dot product of the transposed weight vector and a data point is 0, where are those data points? If you choose them as vectors. This line goes through the origin. Perpendicular? Yeah, so they're on this line here. This line, I'm sorry, I should have put a coordinate system here. So if this line goes to the origin, the data points for which this is 0 here lie on my separating hyperplane. They're perpendicular to W. So, and then, in addition, so my W gives me the orientation of my hyperplane. And then I can have a bias. And the bias shifts the hyperplane around. So in this case here, this formula holds. I'm assuming here that W is normalized. So the length of W is 1. So this is your formula for your hyperplane. And all you need to think about is you have your W to say which orientation the hyperplane has, and you can think about B shifting the hyperplane around. So if you now think about your 2-point clouds, what you want to do is you want to wiggle W and B in a way that you get this hyperplane in between your 2-point clouds, right? This is the goal if you want to learn a separating hyperplane. So all you have to do is to tune W and B in the way that you end up in the middle of those two data clusters. And then once you have that, then prediction becomes really easy. Because all you have to do is you evaluate your equation, right? You take your new data point, X, and you do the transpose weight vector dot product, and you add your bias term, and then you can just see whether the result is greater or smaller than 0. If you're greater than 0, you're on this side. If you're smaller than 0, you're on this side of the hyperplane. So for this classifier also, once you have optimized your W and your B, you can throw all the data points away. You just need to remember W and B, and you can classify all the new data points coming in. Does this make sense? So this is quite simple, right? It's basically a weight vector and my bias, and it's just a line in the 2-dimensional case. But this caused actually quite a stir when it was invented, because it's a perceptron. What you can see here is, this is just the definition of the dot product. I have x1 as my first feature in my sample X, and I have w1 as my first entry in my weight vector. And what a perceptron does is, it multiplies x1 with w1, x2 with w2, and sums all of this up, and then sees whether that is greater or smaller than the bias term, which you can basically think of, you multiply these two, you sum them up, and you subtract b, and then you see whether that is greater or smaller than 0. And then you know whether your neuron fires or not. And this is why this caused such a stir. So, because this is a mathematical model, a simplified, but a mathematical model of everything that is in your brain, kind of, right? It's full of neurons. Neurons is what enable us to learn, and this is the model of a neuron. You have a dendritic tree. This is where the input comes in, here. Those are your axes here. Those are the signals from the other cells out there. And then you have your cell body that kind of collects all the signal, right? And if it gets enough input signals from all its dendritic arbors, it's going to fire along the axon. And this is the idea here. If the sum gets large enough here, of those products summed up, then it fires and gives you a 1 for your class. So this was invented quite a time ago, 1957, by Frank Rosenblatt. And I just think this is a fun fact of history because he gave a press conference on his perceptron machine, and the New York Times reported afterwards, it's the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Because it's a neuron, right? And this emulates how people think. But we've seen the math before. All it is a separating hyperplane. But this is really, I think I linked the Wikipedia article here. This is really a fun history to read, like how the field of AI started and then ramped up with this, and everybody was excited. And then Minsky came and said, wait a second, don't get too excited. And he said, what about the XOR function? And what you can see here is the so-called XOR problem. It's a binary Boolean function. And what it does is, if you have both of your features 0, or both of your features 1, then it says 0. And if they're different, so if you have 1, 0, or 0, 1, then it is a 1. Right? This is the normal XOR function that you know from an introduction to computer science. So I have my two classes. In this case, I only have 4 data points. What is my perceptron going to do with this problem if I say, please classify in those 2 classes? Yeah?
Well, if you only use one perceptron, it's going to get confused.
Yes. The perceptron is going to get utterly confused if you just use 1. Why? Yes, try to draw a line here. The perceptron, all it can do is draw 1 line in that space. There's no way you can draw a line here and not make a classification error. Those are not separable. Those are not linearly separable. So they pointed out this great, great weakness, and everybody got really disappointed. So disappointed that funding sources were cut. This is called the winter of AI. Like, it's a bit more, you can see the whole history in Wikipedia, but this is kind of what it boils to. There was a big excitement, and then people realized all the limitations that these models have. And even the biggest advocate, actually, who pointed this out already kind of knew the fix. And we're going to talk about the fix later. But still, I think also the original paper from those guys is really cool to read. Like, they have appendices at the end, what they thought all the implications are about the brain working and memories. Is fun to research. So there actually is a quite easy fix to this problem, and that is we add another dimension. So I'm just adding a third feature here. And what I'm going to do is I'm actually going to compute the XOR function on the input. What that does is it rises those 2 points up, right? Because the XOR function was 0 for these 2 guys and 1 for these 2 guys. And what you can see now, in 3 dimensions, I can actually put my separating hyperplane between those. So by casting my problem into a higher dimensional space, I made it linearly separable. And this is one of the tricks that support vector machines also use to get really great classifications. Does anybody not understand what is happening here? Are there questions? Right, so all it did was I just computed the XOR function. I basically got a third dimension for my data points. Right? This guy is now 0, 0, and 0. And this guy is 1, what was it before? This guy is 1, 0, 1. And this is why it rises up. Yeah? Yeah, okay. This is just an example how you separate this. In the praxis, it won't be the function that actually gives you the label. You're right. Yeah. This was just meant to give you an insight into how you can solve this problem. We're going to see later how you do this with actual kernel functions. Just to give you an idea how this could work. So support vector machines in general are widely used for all sorts of classification problems. And I know that Isabelle Gouillon has a list with applications. I'm not sure whether that is still maintained. I think it might be a bit outdated by now. But it still can show you that there's a wide range. Like if you look there are projects from chemistry over biology over text classification. So support vector machines really have been used all over the place in every application you could basically think of because they performed very well. They still perform very well. So, and this is why some people say, if you have a classification problem, try the support vector machine first. There are other people who say the same about the random forest. This is why it was most important to me to introduce you to these two classifiers. So the other thing a support vector machine uses is maximum margin classification. What that means is, if I just use a perceptron, what you've seen before, just this one hyperplane, both of these actually do not make classification mistakes on my training data, right? I could end up with this line. I also could end up with this separating line. If you would draw a line, which one would you choose? Would you choose A or would you choose B? A. Why? Because I have the maximum margin. So if I draw the margin here, and I apologize, I did this by hand. This is slightly off. But you can imagine this being in the middle. You can see that there is basically more space to the nearest data points here between your separating hyperplane and your points and here. And why do I prefer that solution? The idea is that you haven't seen all the data points, right? You want to do prediction for the next unseen data. And if a point ends up here, I would still like it to be classified as yellow and not as blue, right? So it's kind of giving you a robustness by having a distance, the maximum distance to both of your data clusters. You're trying to be robust in the predictions for new data points. What this is really, really helpful for is if you have a lot of feature dimensions. So this is where support vector machines really shine. Most classifiers are starting to give up if your number of features is greater than your number of samples. Like then you're in deep trouble. Support vector machines might be able to still help you there. So if you have such a problem, go for a support vector machine because this max margin really is introducing robustness in those high dimensional spaces. And this also means that we basically do not care about all these other data points. What we really care about is the points closest to the separating hyperplane. When I first heard about support vector machines, this was very surprising to me. Because what does it mean, right? I mean, it makes sense. If I just want to optimize the margin to my separating hyperplane, these don't give me any information. I'm only interested in the points that actually are close to my hyperplane. If I delete this point, this decision line doesn't change. Can you see that? Like I could get rid of all of these. If I keep those two, I get the same solution. This is kind of weird because when I thought about learning, I always thought when I want to teach someone something, right? I want to teach my apple-orange example. I'm going to show them this is the ultimate apple, right? This is what an apple really looks like, and this is what an orange really looks like. And then I assume from these really good prototypes, they're going to learn to separate the classes. Now, the support vector machine just intuitively the opposite thing. It says, I don't care what the ideal apple looks like, and I don't care what the ideal orange looks like. Show me the apple that almost looks like an orange, but still is an apple, right? It wants only to see the cases that are hard to classify. So this also makes it very nice for predictions later on, because you're going to see it then also like encoded is only, the separating hyperplane is encoded only in those support vectors. This might look like I need only very, very few data points to learn a support vector machine. And I said, yes, it can still rescue you even if you have a lot of feature dimensions. Why do I still want a large data set here? Not like super crazy large, but more than 2 or 3 points. Like when you collect your data. Yeah? Yeah, and something even more, like if you think about maybe the ideal apple being here, and you have kind of a Gaussian distribution, maybe of your features around this, then those guys are going to be rare, right? If I show you 10,000 apples, most of them are going to look like apples, hopefully. And the guys that actually are easy to confuse with an orange are going to be sparse. So this is why you still want to collect all the data, because you need to find good support vectors here. But once you have those, you basically don't care much about the other data points that you have. So a bit more math to give the intuition how we find that separating hyperplane. So we said for the points directly on the separating hyperplane, this equation equals 0, and then I can classify my data point depending on whether this is larger or smaller than 0. So now let's say we have a data point that lies directly on this margin. So this is my margin there, and what I do is I project now this data point down to my separating hyperplane. I call that x bottom. And the margin I'm now just going to call gamma. So this is my margin here. I have my data point x here. And to go down on the separating hyperplane, I'm going to use my w vector here. What I'm going to do is I'm going to flip it to point into the other direction, right? I want to go from that point to the separating hyperplane. I know w can get me there. I just need to flip the orientation. So this is why the minus comes in here. And I'm going to normalize it to a length of 1, because I want my gamma to say how far I go, right? So my margin here is gamma. W is giving me the direction, and I go from x with gamma times the normalized version of w, and I end up on the orthogonal projection on my separating hyperplane. Now I know that this point here, x bottom, lies on my separating hyperplane. So I know that for this point, this equation here holds. So w transpose times x bottom plus b equals 0, right? So what I can do now is I'm just going to take this part here and plug it in, substitute it for x bottom. And then I'm going to solve for gamma. This is all that is happening here. And then I have now a formula that gives me the geometrical margin. So if I want to express the size of the margin in terms of w, x, and b, this is how I can do it. And you can see this is normalized by the length of w here. Now, this works if my x lies on this side of the hyperplane, right? But I'm also going to have points that lie on this side. And what I'm going to do is I'm just going to multiply, because I really just want to care about this side. What I'm going to do is I'm just going to multiply this by the label. Because this, we said, is the positive area, right? And the label is either plus or minus 1. So if I multiply by plus 1, nothing happens. If I have a point that was on the other side, and I multiply by minus 2, I actually just flip it over. So I'm here again. Right? So all I have now is really an equation that gives me gamma, the geometrical margin. I need to care about this because this is what our max margin classifier should care about, right? I want to make gamma large. So, and now I'm going to introduce the functional margin as well. And this is basically just the geometrical margin without the normalization. So the idea just is your geometrical margin, you can scale w and b together. If if I say W is 2 times W and B is 2 times B, right, then I also have a 2 here, and that would cancel out. So I can scale those, and my gamma doesn't change. That is not true anymore if I skip the normalization. In my functional margin, if I scale W and beta, then my functional margin becomes larger. And this is just for optimization reasons, because what you're going to see here now is this is what we ultimately would like to do here. I want to maximize the geometrical margin. You see here the I is missing. What this is supposed to mean is this is the minimal geometrical margin. So from all my gamma I that I have, from all my data points, I take the smallest one, the one that is closest to my separating hyperplane. And this distance I want to make large. So that is my maximum margin. So I want to maximize the minimal geometrical margin. I want to maximize the distance of the closest data point. Subject 2, and now this is my misclassification rate here, right? I want that, so Y again flips the point. If it is on the wrong side of my hyperplane, it flips it to the other side. And here I look on which side I am. And this should be greater or equal to the margin I have. So I want all the points to lay beyond that margin if they are classified. And now I just say, with the condition that W, the length of W is actually 1. And I do that because then those two are the same. Right? If this becomes 1, then they actually are equal. But this is non-convex, so that is not very nice. So this is just a copy from before. So if you want to know even more detail of this, I want to give you a head start here. If you want to read up more on this, Andrew Ng. This is the notation he uses, and I'm using it on purpose because he has, I think, a whole lecture only explaining the math behind support vector machines. If you really want to go into those models, that's a really cool resource. I have the link coming up later. I just want to give you a feeling for what is happening here. So if you don't understand all of that in great detail, it's fine, but I want you to know a bit what is going on. So this is a non-convex optimization problem. We don't really like non-convex optimizations because they're really hard to solve. So what we can do instead is we're now using the functional margin here and normalize it. Here. This was my geometrical margin that is normalized, and I said the functional margin is basically the same, it just misses the normalization. So now we exchange the two and put the normalization here explicitly in. And we keep our misclassification rate with the exception that this now again also is the functional margin. What we did here now is we got rid of this constraint. But this is still not very nice to optimize. So what we're going to do in the next step is we just did this because we said the functional margin can be arbitrarily scaled, right? So what I can do is I can just set this to 1 because it doesn't change my my optimization problem. And then you have 1 over the length of W, and maximizing that is the same as minimizing W itself, and we take the square here. And now it's a convex optimization problem. That's the nice thing about support vector machines. You need to do this massaging. There's also a bit of relaxation going on, but you end up with a convex optimization problem that you just can plug into solvers out there. So you don't need to program stuff here. You can just use commercial quadratic programming solvers, and they're going to give you the solutions for this. So they're going to tell you this is the W you can use and the B. So what does this mean in praxis? I think I had this open already. Oh, now it actually works. Ha! I had a bit of problem with Java earlier today. So this is just a small applet that I like to use to demonstrate how support vector machines work, and I can just put arbitrary points here. No. Let's come up with the, oh, actually, yes. Kind of a 1 point cloud here. And then we have a 2nd point cloud here. And now I'm just going to say, give me give me the separating hyperplane. You can see here, this is our decision surface, right? Our separating hyperplane. Here's the margin. And then here, faintly, you have an outline around the support vectors. So here, from all those data points, it actually only picked 3. And now you're going to see a weakness of this type of formulation, because if I just put one data point here and I recompute, everything changes. Right? I said before, support vector machines are robust, and that is very nice with this max margin property. And I just had to put one more data point, and my whole classification surface changed. That doesn't look very robust, does it? So the solution here that people came up with are so-called slack variables. So what I'm going to do now is I'm going to allow the support vector machine to make mistakes in the training data. So you can see one of those yellow data points ended up here, and one of the blue guys is up here. But I still am saying these are the support vectors. It doesn't try, it couldn't even fit something here that is linear. So what you do is you introduce these slack variables in the quark C in most formulations, and you just say, OK, this is the distance to the margin where it actually should be. Right? This yellow guy should be on the other side. And I'm going to penalize this but with this slack variable. This is the length. You can see if this would be even further in, then C would be larger. Right? So the more severe my misclassification is, the more slack I need to give to the support vector machine. And what this does is it changes my optimization problem. And now I'm not only minimizing over W, but I add this term here. And you see there's a weight on this term that is called C. And this is going to be important if you use the support vector machine. You often need to tune the C. And this is where it comes from. This is the weight over your slack variables. What it's saying is I want to minimize the length of all those slack variables. I don't want points that are very, very wrongly classified, that are very, very far from the separating hyperplane on the wrong side. And then the rest is unchanged as before. So now this is, oh wait. Now it deleted my result, darn. This is the C that you saw in that formula. So if I come up with my problem again, and I have my data points here, no, it's not working anymore. If I have my data points here and my second class here, I can compute the result, can put an additional data point here, right? And it changed everything. And now I'm going to reduce the C. What this means is I penalize less for the slack that I'm giving. Oh, didn't change it? Let's make it small. And you can see it gets more robust here. Like now it's actually allowing you, see, it doesn't really misclassify points, but what it does is it allows support vectors to lie inside the margin. Right? This is already giving slack, because the slack is computed with respect to the margin lines and not the separating hyperplane. So this makes your whole prediction more robust. And this is the C is also in the cycle-Duran classifier, so this is what it does.
What sorts of ranges does the C value have?
I'm going to show you. There's a great paper. I have the reference in here. That is one of the problems with support vector machines. The random forest I did first because you basically don't really have to tune many parameters. With the support vector machine, you need more insight into what is actually going on because you need to tune those. Easiest is to do grid search, but you need to have a sense, at least, of the values you're trying. One thing that I can already say is it's a good idea to have exponential steps. So you can see here it's 10 to the minus 1, 1, 2, 3. So you wouldn't go like C equals 1, 2, 3, 10, 20. You would go 10 to 1, 10 to 2, 10 to 3. So try exponential steps. I would say they're actually less prone to overfitting in a sense because they're linear, and this max margin can give you, the question was whether I would say that support vector machines are even more prone to overfitting because you have to tune more variables. I would say they should be less prone to overfitting because they're linear classifiers, and they have this max margin property, gives you robustness, but you need to take care how to tune those parameters. So you want to do cross-validation here. Yeah, if you do that carefully, then they can have really, really good results. So, no, thanks. So I'm introducing slack variables here to make my decision boundary more robust. And then in addition, now we had this XOR problem. One up there said very well, if you already know the XOR function, you don't have to build the predictor in the first place, right? So the truth is that you're using different functions. And this is how you would normally do it. Like, this is a problem here that is also not linearly separable. I use just one dimension here. Those are my points. There's no way I can put any line in here. So and now what I'm going to do is I'm just going to project those points onto a parabola. All I did here is I drew a parabola, and then I just put the points up. What you can see now is now it became linearly separable in 2D. So did I add any more information here? Yeah? Yeah, it looks a bit like there is more information. The question is just where the information really lies inside there. Yeah?
Yeah, I mean, maybe you had some insight into how the original data was laid out and changed how you looked at it?
Yeah, so I maybe had some insight how the original data was distributed and tried to use that here. In most cases, you actually don't. You go blindly and just optimize your parameters. I think there are rare cases where people actually knew their data that well that they came up with some do. Some even have kernels that they write for their specific problem. So yes, absolutely. In those types, you put in more information. If I use such a generic function as a kernel, I wouldn't really say I added more information. But what you would normally prefer is if I compute that XOR function, I already know that is giving me my label, right? That's the ultimate information that I induced there. I induced the label into the problem. If you have, we talked about the Google car. If you can measure more to make your problem linearly separable, I actually would prefer that, most probably. That really adds information to your data, right? This is more putting this into the classifier, massaging your data, trying to separate the points more using higher dimensions. This is actually, where the curse of dimension kind of helps, right? Because on one hand, you're casting your points into a higher dimensional feature space. We said that is not a good idea to have too many dimensions. In this case, it helps because it separates the points and makes them linearly separable. This is the way to think about this. And this is just a visualization that I thought is really cool that I found online. And this shows this for the three-dimensional case. And what you see here is there's a couple of blue points here and all those red points around it. And he now casts it into 3 dimensions. And this is, again, a parabola, I believe, just in 3 dimensions. And now comes the separating hyperplane and cuts off the blue points here at the tip. And I think for me, the aha effect came when he projects this down again, because here you see that you can even have a decision boundary that is a circle around your cloud of blue points here, right? But as before, all you had was a separating hyperplane. There is no circle built into your boundary classifier. So this is the quadratic kernel. So first you need a function. So you have your data point. In this case, it's only two-dimensional, so I have x1 and x2 in my data point, two features. And what I do is I have a function phi to expand that data point into this higher dimensional space, right? And what you see is it's just computations. So it's like I have just x1 and x2 here, and then I have the square of the two, and then I have the multiplication of the two. This is just a polynomial expansion of the data point here. And I could do that for even more dimension, and then you would have like to the power of 3, to the power of 4, and all those other terms there as well. And it gets very, very long very, very soon. Is there a question? Sorry, yeah?
Sorry, I'm still confused as to whether or not you add information, because like in this context, it seems like, oh, I just arbitrarily am taking this phi
Yeah.
and plotting the points onto that. That doesn't seem as insightful as when we saw your picture. It looked like you sort of projected them based on the order that the points were occurring onto different places in the parabola. So like, what would you say? Like, are you adding information or no?
In this case, I would actually say no. This is very similar to this three-dimensional case, because I'm just using this generic parabola kernel. I'm not saying it has any relation here to the problem I'm describing. And as you see here, it's really just the expansion of the points onto the parabola. That's all that is happening that I need here to separate the points. But for me, I mean, that is kind of provocative question. What I wanted is I want you to think about these things. And like, it's not a total answer, right? I could come up with a kernel that would exploit things I know about the data. And then you could say, I induced information into my classification problem. If I use such a generic kernel, I would more say I applied a nice trick to make them separable. So we just have this function phi here. And this is kind of rising these points into these higher dimensional spaces. And now the support vector machine is going to look for similarities between points. This is what it's going to care about. It wants the distance between 2 points. And so you can just compute the dot product between the expanded points. Now you can see that this gets computationally expensive, right? I only had a two-dimensional problem. Even for a very low-grade polynomial, this gets very expensive very fast. That is not the reason people are so excited about support vector machines and kernel methods. The reason they're excited is this. I can get this really, really expensive to compute similarity measure with just the 2D points. There are certain functions that allow you to do this math trick. I don't have the real math here on the slides. You can actually try and look at this. I can also maybe, if you're really interested, show you more about this next lecture. But you have this function here, and in principle, you have your points. You only care about how close or far away they are. And you put them into the higher dimensional space, and you want to know in that higher dimensional space how similar they are. And kernel functions allow you to compute the distance in this high dimensional space with just the two-dimensional points. And this is what all the hype is about. So I spend very low computational cost to compute the similarities in a very high dimensional space. And this is what makes kernel functions so useful. And this is the quadratic kernel. You can generalize that to polynomial kernels of different degrees. Right? You just need to put the degree up here. You can imagine this formula here getting really, really long for higher degrees of the polynomial. Yeah?
So the classifier will change based on the function you use to project into
Yes.
a higher dimension?
Exactly, yes. This is one of the parameters to choose. Yes, it is kind of arbitrary. That is true. So what people do there is they just believe other people who have used a lot of support vector machines and did a lot of experiments. And what those people are going to tell you, use the RBF first. But yes.
Also, why were you going from 2 to 4 dimensions instead of 3? It's just like a...
This is, so the question, sorry, the questions before was, this is kind of arbitrary which kernel to choose. And the other question is, how do I choose my S here? And the answer is that it's yet another parameter for your grid search. Yeah, this is all you do with support vector machines. Like you have to tune a lot of these parameters.
The RBF is pretty susceptible to overfitting.
What?
The RBF overfits.
The RBF overfits. The RBF has a very high chance that it could overfit if you don't do your cross-validation carefully, because in principle, the higher dimensional space it can project to is infinite if you choose the parameter right. This is kind of counterintuitive, right? Like in that high dimensional space, I get in an infinite dimensional space, I can get the similarity between the 2 points by just using the RBF function. And I only can do that because I never actually have to compute the representation of the points in this high dimensional space. So I'm going to let this miracle occur here. I just wanted to give you an intuition why this is so important for the support vector machine. So this is the optimization problem we talked about. And I like this cartoon here. So he goes with this formula, and then he says, then a miracle occurs. And he says, I think you should be more explicit here in step 2. I'm not going to be more explicit here because step 2 involves Lagrange multipliers and Karush-Kuhn-Tucker conditions. If you know what those are already or want to know more, I really, really recommend Andrew Ng's course. Like it's on iTunes University and YouTube, and I think it's also Coursera course. Like he has a very gentle but thorough introduction of the math. I'm not going to do that. I'm just going to show you the solution. And so this is the dual formulation of the problem. And the thing to care about for you here is, here are dot products, right, of my points, the similarity between the points. And here's where the kernel comes in. So here I have just the dot product between xi and xj. These are 2 of my data points, right? And they don't appear anywhere else here. So the only version where they appear is within a dot product. And I've seen that this dot product I can compute with the kernel in my low dimensional space. And this is what makes this so useful. So here's just the reference if you want to read more about this. Let me see. Let me just shortly check. Yeah, I'm going to go until there. So this is the kernel trick for support vector machines. You have the kernel trick and you have your maximum margin, and they work together, right? I can do the kernel trick with this high dimensional feature space because the max margin makes me kind of robust against these high dimensional spaces. And thankfully for the kernel trick, I have little computational cost behind this trick. Yeah. Oh, and then I'm going to show you the applet next time to do a short repetition of what we talked about today. I'm just going to show you the tips and tricks. Because important, if you want to use a support vector machine, we've already seen you will have quite some parameters to tune, right? You have the kernel you need to choose. The kernels come with their own parameters. You have the slack variables that you need to take care about. And on top of all this, support vector machines are not scale invariant. We said that one of the cool things about the decision trees, and due to that also the random forest, is it only splits on this one feature. So I could have categories and like continuous features, and I didn't really have to care about this. A support vector machine will even care if you have all your measurements in centimeters, right? And then one of the variables is in inches. This is going to influence your result. You need to normalize data that you put into a support vector machine. So you need to check by whatever library you're using whether it normalizes by default. I believe scikit-learn doesn't. Does anybody know evidence to the contrary? I think they don't. So normalizing your data, you can do mean 0, standard deviation 1, or you can try and map everything into a common interval. This also might be a subject of your exploration to make your classifier work very well. Important, you need to normalize your test set in the same way. We already said that for the centering for SVD, right? If you, for example, want to normalize mean 0 and standard deviation 1, you estimate the mean of all the features on your training set. And you never, ever do that on the test set. And you subtract all the means from all your training data and also this mean vector is what you use to subtract, to normalize all your test data points. So do not estimate new means for the test data. You basically want the test data to go into the same normalization space as your training data. So do not re-estimate the means there. And this is really, if you want to use support vector machines in any of your projects, I would highly recommend reading this. This is a practical guide to support vector classification. So they give good default values, intuition, and what you can do to address this tuning problem. So, and they say normally it's recommended to start with the RBF kernel and then try exponential sequences. Also for the RBF kernel is going to have a gamma that you need to tune. So also go with exponential sequences there. Okay. Questions about support vector machines so far? Yeah? If you have categorical data, you're pretty much screwed. Yes. What you can try maybe is this one hot encoding, where I showed this for the decision trees, I think, where we had like male, female, and infant. And instead of having the categories, you had 3 Boolean variables that were true for either of those, depending on which one, because this kind of converts it to numerical data, but I wouldn't really do it, I guess. Especially not if you mix the two, like if you have categories and numerical values. Okay, then see you on Thursday.